Hello. Good evening, all. I think we can start the class now. So before going into the today class, we can first review the what is the class is taught by sir. Okay. So this week is all about the welding cracks. So the development of the cracks during the welding is one of the primary concern in the welding. Why the cracks are appear is that there is the once we do the welding process during the when the metal get melted and once it is getting solidified during the melting part the volumetric expansion will take place during the when cooling it will start reducing its volumetric volume. So once it is solidifying, the residual stresses will start generate. So once the residual stresses are generating, if the stress amount of the stress value is more than the yield strength of its ultimate strength of the material, the crack it will start break and it will crack will start appear. So this kind of cracks we can see mostly in the case of stress of tensile stresses. Okay, not compressive stresses. We do not see this kind of mm, much problem. Okay, cracks occur when the stress at the point in the weld mate exceeds the tensile or shear strength of the base metal or weld material. Okay, tensile cracking are most common, while the shear are often occurs at certain angle to the tensile cracking. So the cracks only appear when the tensile shear stress are present. Okay, once the crack started, it continues until the stress causes the crack is relieved. Okay, next, what is the different kind of classifications? What is the different kind of cracks are there? Is that there are plenty of classifications are there, or broadly we can say like hard cracks, cold cracks, and liquidation cracks. Hard cracks means it is hard cracks are occurs in the molten the weld bit. Okay, cold cracks which are due to the hydrogen embrittlement and so on. Okay, and liquidous cracks. Longitudinal cracks means it will occur in the longitudinal direction of the weld bit, and transfer cracks it is the perpendicular to the weld bit. Okay, and crater cracks occurs. So if you consider this is the weld bit, this is the base material, and this is the weld bit. Okay, if the crack is occurring in the parallel direction to this valuable, it is called as a longitudinal cracking, and if it is happening in transverse direction like perpendicular to the weld direction, it is called as a transverse cracking. Okay, so crater cracking is that there is a certain region where it will crack will start and it will propagate in all directions. Okay, so you can see those cracks are here, as you can see here. So this is the crater cracking. So here is we have a one crater will start, and here from here the it will start crack propagating in all direction. Okay. Similarly, there are other cracks, and next underbraid cracks and toe cracks are there. What are those? Is that underbraid means suppose in case of pellet welding. So if is the this is the weld, so the crack will appear below the weld bit. Okay, in the base metal region, it is called as underbeat. So toe cracking is that at the edge of the between the toe here weld bead and the base metal, here it is having the toe cracking. Okay. Okay. Next, chevron crackings. These are the happens when it is the cracks occurs. You can see here the chevron crackings. And this is the laminar cracking. Laminar cracking occurs because of the during the in the rolling direction when the grains hardened particles are segregated to the grain region. Those will become less strength compared to the grains. So there the it is in laminar form. It will forms as a crack. This is called as a laminar tearing or laminar cracking. Okay. Similarly, the hydrogen induced crackings are nothing but a cold crackings because of the hydrogen inclusion, and followed by rapid solidification. Because of the rapid solidification, it cannot be the hydrogen cannot be gone escape from the metal matrix. So that results in the hydrogen embrittlement. Okay. Next, what we have seen in the class during our class. So what is the factors which leads to the cracking? One is the solidification because of the faster solidification and so on. Next, segregation of the elements. Suppose if we have a alloying element, as we seen during the undercooling times, so solidification happening during the solidification, the segregation is happening, the alloying elements. So that time, which the regions which are strength will be changes because of the alloying contents. When during the solidification time, the stress is generated, which results in the cracking in the those segregation regions. Or in the is the third is the residual stresses, and the because of the intensity of the residual stresses is increasing, the it is higher prone to cracking. And the metal thickness is higher, so it will results in the faster cooling of the material, then which reduces the cracking and restraints. So if we do any fixturing and so on, the fixturing will results in the stress generation, the stress which results in forming of the cracks. Due to restraints, which kind of cracks we can see is that we can see the transverse cracks mostly. Okay. And weld bead shape, the what kind of weld bead shape we are using, like concave or convex. If we use the concave, the crack propagation is much more higher compared to the convex one. These are the factors which affects the kind of cracks which are forming. Okay. So ideally to avoid the crack is that we should have a width to depth ratio more than the 2 by 3 percentage, so that to crack propagation we can be avoided. And metal composition, suppose if metal having the hardenable metal elements, which will results in the crack, uh, more crack propagation will be much more higher in that cases. And welding procedure, which if we do the high speed welding and longer arc length, in that case crack formation is the much more prominent. And the mm, and the pure fit up, and if we do not do the fixing and so on properly, then it is also results in the crack formation. Okay. So liquidus cracking, it happens in the HZ region. It is not in the well bed. It is happen at the HZ region. It is most probably in the SAW, slag welding. In this case, we are giving the lot of heat input. Because of this lot of heat input, the amount of the residual stresses generated at the HZ will become more. That once it is the stresses are more than the its material's ultimate strength, it will start breaking. I mean, it will the crack will start appear. Okay. Next, cold cracking, it is due to, or we can also call it as a hydrogen-induced crackings or delay cracking. It occurs because of the hydrogen in the welding material, and it happens after cooling happen. So it is not immediately we can see the cooling. It is delayed cracking. It happens later part of the time. Okay, it is due to the once during the welding process, if there is moisture is there during the welding process, during moisture nothing but a H2O, the hydrogen is coming from that moisture and enter into the material. Okay, so it happens relatively at the lower temperatures, that is around 200 to 100 degrees centigrade. Okay, so with this we can see the first class some problems. Okay, which of the following is the primary driving force for the crack formation during the welding? Okay, what is the primary driving force for the crack formation? One is the grain growth. So during the welding process, grain growth is happens. It happens in the columnar grains and so on, but that is not the reason for the formation of the crack. Second is the residual stresses. Yes, residual stresses. And third is the phase transformation. Fourth is the alloying elements. So answer will be, it is the residual stresses. Why is that? Welding involves localized heating and rapid cooling, generating the higher residual tensile stresses. Those stresses exceeding the local strength, initiating the crack, especially in the restraint joints. Okay, so because of during the welding process, we do the rapid heating and followed by rapid cooling. Because of that, residual stresses will generate. If the stress value is increasing more than it uh, material shield strength, ultimate strength, so then the crack will start initiating. Okay, so that is the reason. And phase transformation allowing elements, those will not be affecting the crack propagation, the not the primary force. Uh, Next is that hard cracking or solidification cracking may occurs mainly during solid state cooling, liquid to solid transition, recrystallization, post weld heat treatment. Answer will be liquid to solid transition. Okay, explanation: hard cracking forms in the moisture zone during the solidification, where liquid film exists along the grain boundaries and can't withstand the tensile stress. Okay, so it happens. How is that? So during cooling process, you can see here. So once it is this is in a liquid state. Once it is starting cooling, so solidification start from the heterogeneous nucleation start from the this grain boundaries. Okay. So here at the where the HZ, where this liquid pool is contacted with the HZ, I mean heat affected zone. Okay. Once it is starting, it cooling, and once during liquid state the volume is occupying more, but when coming to solid state the amount of the volume per unit material is less. So once the solidification happening, the amount of the material available here is the less, and because of that, the remaining material once it is started solidifying, the lot of tensile stresses will generate between this, so that will result in the immediate cracking because it is the having the less strength at this region. So that results in the this solidification cracking. Okay, it is increases with the once we have the sulfur enriched film. If we have the sulfur phosphorus in our material, that will further promote this kind of solidification cracking. Okay, so this is how the solidification cracking looks like. Okay, next is the which of the following element increases the susceptibility to hard cracking? Answer will be option A carbon, option B sulfur, option C chromium, option D nickel. Answer will be sulfur. Sulfur forms the low melting point compounds like iron sulfate, promotes the liquid film formation at the grain boundaries. Okay, that increases the hard cracking risk. Next, cold cracking in welding is most commonly associated with the, what is the reason of the cold cracking? A, high welding speed, B, hydrogen presence, C, low cooling rate, D, grain coarsening. Answer will be hydrogen explanation. Okay. So why? Because cold cracking means it is due to the hydrogen explanation we have seen here. So because of the hydrogen entering, it is from the, if there is any moisture is there, from the moisture hydrogen will enter into the material, and it is happen at relatively low temperature at 200 to 100 degrees centigrade. Okay. So answer will be the B. It is the hydrogen presence. Next, which microstructure is most prone to hydrogen induced cracking? Okay, which is it? Option A, austenite, option B, ferrite, option C, martensite, option D, perlite. Answer will be option C. Because martensite is the hard and brittle phase, which is the, so it has the low hydrogen solubility. So that if less hydrogen solubility means it will be segregated at the grain boundaries. So the grain boundaries accumulates the higher concentration of hydrogen that will initiate the uh, hydrogen embrittlement followed by crack uh, formation. Okay, so answer will be the martensite. So laminar tearing occurs primarily due to higher sulfur content throughout the thickness strain, rapid cooling, and hydrogen embrittlement. Answer will be throughout the thickness of the strain. So, how the laminar tearing happens is that during laminar tearing occurs in the roller plane due to the weak inclusions like magnesium sulfate aligned in the parallel to the rolling direction when subjected throughout the thickness of the tensile stress. You can see the this laminar tearing process here. Here is the laminar stresses. So during the rolling direction in the base material, here the it will be takes place. So when this kind of brittle phases form like manganese sulfate, iron sulfate, and so on, those will have a less strength at the grain boundaries to accumulate. Those will start fracture and creates a in parallel laminar direction, laminar cracking. Okay, you can see here also it is happen, laminar tearing happens in the base material region. Okay, so it is the throughout the thickness of the strain. Uh, Next is the which of the following crack forms after welding often delayed. So delayed cracking is nothing but a hydrogen embrittlement cracking or hydrogen induced cracking or cold cracking. So option is the A hot cracking, B solidification cracking, C cold cracking, D liquidation cracking. So answer will be the cold cracking, nothing but a hydrogen embrittlement cracking. Okay, so answer will be C. Cold cracking can appear hours or days after the welding due to hydrogen diffusion and residual stress buildup. Okay, so liquidation cracking occurs in which zone? So liquidation cracking where it will occurs, as we seen here, it is occurs in the HZ. Okay, due to the it is most prone in the high heat input welding process like SAW and slag welding processes. Okay, and with a high aspect ratio of S&P, sulfur and phosphorus, if those are more ratios are in the steel, then it will be results in the liquidation cracking. Okay, so answer will be the it will be the HZ. Liquidation cracking occurs in the HZ due to partial melting of the grain boundaries constant during the welding thermal cycle. So which parameter reduces the susceptibility to hydrogen cracking? Okay, so how we can prevent the increase the hydrogen prevent the hydrogen cracking is that option A high increase the cooling rate, option B preheating, option C increasing the sulfur content, option D reducing the heat input. Answer will be preheating. Why is that? Preheating reduces the cooling rate. So once the cooling rate reduces, there is enough time to hydrogen to diffuse and escape from the weld material. That's reduces the also it reduces the formation of the martensitic phase, because martensitic has a less ability to diffuse the hydrogen. So that results in the less hydrogen cracking or cold cracking. The Mosey zone during the welding refers to, okay, fully liquidous region, fully solidus region, partially solidus region, or heat affected zone. Answer will be it is the partially solidified region. Okay, the Mosey zone contains the solid dendrites plus liquid film, makes it highly susceptible to solidification cracking due to the weak grain boundary strength. Okay, why it is having the weak grain boundary strength? Because of undercooling, the segregation will take place. Any brittle phases will form at the grain boundary region that will uh, results in the cra- uh, cracking formation, crack initiation. Okay, so for some of the key concepts, like from the first lecture is the first lecture of this week is that hot cracking occurs during the solidification, cold cracking occurs due to the hydrogen embrittlement or martensitic phases and stresses. Okay, and liquidous cracking, it is in the HZ region. It is occurs in the HZ region, not the weld material. Okay, it is occurs in the high heat input welding processes. And laminar tearing, it is inclusion throughout the thickness strain. It is occurs in the rolling direction, and residual stresses is the main driving force for the this crack propagations. Once the residual stress value is um, exceeding the material's ultimate strength, then the crack will start propagating. Okay. Next, coming to the what is the uh, types of uh, cracks are present. Okay, so we can see here is the longitudinal cracks, transfer cracks, crater cracks, and underbead crack and toe crack. Longitudinal crack means it is happening in the parallel direction to the weld bead. Crater crack is the, it is like a happening in all direction. Okay, transverse crack means it is happening in the perpendicular to this weld bead. Okay, so crater cracks, there are three types of crater cracks occurs in the weld metal. Okay, one is the longitudinal, transverse, and crater cracks. Okay, crater cracks occurs when the welding is interrupted, and those were usually star shape and progress only up to the edge of the crater. Okay, crater cracks, actually these longitudinal cracks are initiated from the crater cracks mostly. Okay, and from here it will propagate along the weld direction. Okay, crater crack can be, starting point is of the longitudinal crack, especially when it occurs at the end of the weld. Okay, this can be prevented by starting each weld properly and correctly starting the each electrode change point and filling the craters. Okay, longitudinal cratings is generally runs throughout the weld bead in the longitudinal direction. Okay, longitudinal cracks at the surface of the weld metal can be X of the craters started deep down the joint, mostly root joint, and root pass should be therefore made very carefully. So this is the longitudinal crack, and transverse cracks which are happen in perpendicular to the weld axis. Okay, and base metal cracking, these are occurs uh, in the base metal of the uh, workpiece. Okay, so it is not in the weld bead. So we can classify them into two ways. One is the this occurs in base metal usually located in the HZ, heat affected zone. Okay, when the HZ become hard and brittle. Okay, this is normally following types of the longitudinal base metal cracking, transverse base metal cracking, and underbead toe cracking. Okay, so longitudinal base metal cracking is that it is the longitudinal direction to the weld bead, but the cracks are appearing in the base metal region. Okay, similarly transverse base metal cracking is are happening in perpendicular to the base metal region. Okay, underbead means if you see this pellet welding, this is the weld bead and it is happening in the base material, but underneath the weld bead. Okay, tau cracking is the, it is happening at the this interface between the weld bead and the base material. Here it is happening the tau cracking. Okay, so this is the chevron crackings, those we will see later. Okay, now we will see some problems, some problems. Okay, which of the following cracks are primarily intergranular and forms during the solidification? Answer will be A, hard cracking, B, solidification cracking, C, laminar tearing, D, reheat cracking. Answer will be solidification cracking. Solidification cracking occur along the grain boundaries in the weld metal due to the liquid film presence during the final stage of the solidification. I think that we have seen before. So here you can see solidification cracking during the once it is solidifying, the brittle pieces which are the present at liquid stage, because so solidification start from the this boundary region and propagate towards the center region. Once it is reached to the top, because of this brittle phase, this solidification crack will be formed. Okay, next, which crack type is commonly referred to as an hydrogen induced cracking? I think it is also we have seen, it is the cold cracking. Cold cracking nothing but a hydrogen induced cracking. Okay, liquidus cracking differs from the solidified cracking because it occurs in the fully solid metal, weld metal center line, heat affected zone, base metal far from the weld. So liquidus cracking mostly happens with liquidus cracking nothing but it will happens at the HZ, heat affected zone. Okay, liquidus cracking occurs in the HZ due to melting of the low melting constituents at the grain boundaries. Unlike the solidification cracking, in the weld material. Okay, if the like sulfates, iron sulfate, magnesium sulfate, or phosphates, if those are present, those have the less melting point. So those will be melt at the grain boundaries, initiate the cracking. That is the liquidus cracking. Okay, which type of the cracks is the mostly associated with the thick rolled plates containing inclusions? Okay, if the thick rolled plates containing inclusions, which kind of crack it will happens? Option A, solidification cracking. B, hydrogen cracking. C, laminar tearing. D, crater cracking. So answer will be laminar tearing. So laminar tearing occurs due to the non-metallic inclusions like manganese sulfate aligned during the rolling causes weakness under through the thickness strain. Okay. Next, crater cracks are typically found at the weld start, at the weld termination, in the HZ, in the base metal. So cracks where it will be formed at the end of the welding. At the end of the welding, when arc is stopping, there the crater will form. From there, the um, cracks will be started propagating. Okay, the crater cracks forms at the end of the weld bit due to the improper filling and the shrinking stresses. Next, which crack type is most likely to occur during the post weld heat treatment? So during the post weld treatment, I think it is the of the fifth lecture. But however, here we can complete it. So it is a due to the reheat cracking. Okay, reheat cracking occurs during the post weld heat treatment due to the stress relaxation and the grain boundary weakening, especially in the creep resistance steels. Okay, by reheat cracking happen is that we will see once we go there. Okay, so which of the following cracks is transgranular in nature? It is the cracks happening between the grains of the material. So what is that? It is the option A, solidification cracking, option B, liquidus cracking, option C, hydrogen cracking, option D, laminar cracking. So solidification cracking happens during the solidifying of the weld bead. Liquidus cracking at the HZ. Hydrogen cracking, yes, hydrogen is segregating at the intergranular region and forms the cracks. So hydrogen embrittlement it is, and laminar cracking it is happening in the base material because of the impurity. So answer will be the C. It is the hydrogen cracking. Hydrogen cracking often transgranular, propagating through grains due to brittle fracture in hardened microstructures. Which crack type is strongly influenced by segregation of low melting point elements? So because what is the because of the segregation of low melting point elements, what is the cracking? It will be the option A, cold cracking. No, cold cracking is by hydrogen embrittlement. Solidification cracking, reheat cracking, laminar cracking. Answer will be solidification cracking. You can see here because of the segregation of this low melting point elements to the at the end during the solidification point. So this cracks will appear. What is the this low melting point ones are the sulfur enriched uh, elements like iron sulfide or manganese sulfide or other elements. Okay. So next, which crack type is primarily driven by the throw thickness shrinking strain? So it will be the, if it is the throw thickness shrinking strain means it will be the laminar tearing. So answer will be the hydrogen cracking, laminar tearing, crater cracking, reheating. Option will be laminar tearing. So laminar tearing is caused by shrinkage strain perpendicular to the rolling plane, uh, exploiting the weak inclusions layer. Okay. Next, which crack type is most sensitive to cooling rate and hardness of the HZ. So once it coming to the cooling rate, hardness of the HZ, it will be the option A, solidification cracking, option B, crater cracking, option C, hydrogen cracking, and option D, liquidus cracking. Okay. So which is answer will be hydrogen cracking. Why? Because once it mentions the cooling rate means if it is a faster cooling rate, if it is faster cooling rate means it will be the formation of the martensite. If martensitic means it is the increase in the hardness. Okay, if the faster cooling also may forms the hard phase in the HZ, that harder phase, martensitic phase cannot to accommodate the hydrogen that will be segregated to the grain boundaries. The grain boundaries will enrich with the hydrogen that will makes as a hydrogen embrittlement. Okay, high risk so that results in the high susceptibility to hydrogen cracking. Okay, so some of the key points: solidification cracking, where it will happen in the weld material. Key causes is that liquid film, the low melting point film forms like sulfates, phosphates, that will creates the this solidification cracking. Next, liquidus cracking, where it will happen? It will happen in the HZ due to the grain boundary melting. Okay. Next, grain boundary, because of any low melting point phase at the grain boundary, that will be melt and forms the this liquidus cracking. Hydrogen or cold cracking, it will happen at the HZ and weld bead due to the hydrogen and stress and martensitic formation. Okay, so laminar tearing, it is happening in the base material due to the inclusions and the strain. Next, crater cracking at the weld bead end due to the shrinkage. And reheat cracking, crack, it is during the post weld heat treatment due to the it is due to stress relaxation. Okay, next coming to the third one, that is the underbead cracking and toe cracking. Okay, let's see some problem. See, underbead cracking causes primarily observed in the, I think we have seen here underbead cracking. It is laminar. So where we can see where here, yeah, it is the underbead cracking. It is happen below the weld bead. Okay, so toe cracking, it is at the weld bead and the base metal here intersection region is the toe cracking occurs. Okay, so which kind of cracking is primarily observed in underbead cracking is primarily observed in weld metal, fusion zone, heat affected zone, or base metal far from the weld. So answer will be, it is a underbead cracking will be happen in the heat affected zone. That is also part of base material heat affected zone. So underbead cracking occurs just below the weld bead in a heat affected zone, typically due to hydrogen plus martensitic transformation. Okay. Next, the main cause of the underbead cracking is sulfur segregation, hydrogen embrittlement, grain coarsening, oxidation inclusion. Answer will be hydrogen embrittlement. So underbead cracking is a form of hydrogen inclusion cold cracking requiring hydrogen tensile stresses and hard microstructure. So here we get the hard microstructure from the martensitic phase. Okay. Next, trough cracking is most likely initiated due to. Okay. So it is the solidification shrinking, B, stress concentration at the weld toe, inclusion, alignment, grain boundary, liquidation. So what is the answer will be? It will be the stress concentration at the weld toe. So once the uh, why the cracks is forming, it is because of the materials, uh, the stress value exceeding its ultimate tensile stress value. So at the toe region, during the solidification part, there will be the maximum amount of the stress concentration will be there. That results in the formation of this kind of cracks. Okay, the weld toe is a geometric discontinuity leading to stress concentration that results in the crack initiation under the tensile stress. Okay, next, which of the following cracks is commonly found at the root of the weld joint? So root of the weld joint, which kind of one will form? A, crater cracking. No, crater cracking forms at the end of the weld deposition. Root cracking, yes, that could be. And C, toe cracking. No, it is toe cracking happen at the during the fillet welding at the between the weld and base material region. And reheat cracking, no, reheat cracking happen at the anterior region. So answer will be root cracking. Root cracking occurs at the root pass, often due to high restraint. So if we put the fixers are much more higher during the welding process, and hydrogen entering into the weld bead are incomplete penetration. Okay, if there is a not enough amount of the molten, I mean heat input we given, the incomplete penetration of the molten pool, that also results in the root cracking. Next, crater cracks can be minimized by how we can minimize the crater cracking. Increase the sulfur content. No, if we increase the sulfur content, it will result in more crack formation. B, abrupt arc termination. So suddenly, if we stop the arc without in a sudden stop, no, that is also not the reason, not the way to prevent the crack cracking. That will create the crack, followed by the faster cooling results in the crack crackers. C, proper crater filling. So if the crater forming, if we fill it with the material, so that can be, yes, that could be the reason. D, increase in the cooling rate. If we increase the cooling rate, it will become increase the number of residual stresses, that will also increase the cracking, so that is also no. So answer will be C, proper crater filling. So crater cracks due to the shrinkage at the weld termination, so preventing by filling the crater before stopping the arc. Okay. Next, which crack is the most sensitive to joint resistance and rigidity? So which is that? Toe cracking, root cracking, crater cracking, liquidation cracking. So answer will be, it is the root cracking. Okay. So root cracking cracks are highly influenced by the restraint. Restraint nothing but a clamping of the workpiece, which increases the tensile stress at the weld root. Okay. So if we put the restraints, the deflections are suppressed. If the deflections are suppressed, the more amount of the stress concentration will be generated. The more where it will generate at the center region at the bottom, that will be the root crack, that will reach the root cracking. A delayed cracking appears below the weld bead after several hours is most likely. Solidification crack. So here we have to see two things. One is that it is the below the weld bead and it is delayed cracking. So if it is the delayed cracking means nothing but a cold cracking or hydrogen embrittlement cracking. But if the same that cracking happening below the weld bead, it is called as a underbead cracking. So solidification cracking, no. Crater cracking, that is also no. Solidification cracking at the center of the weld bead. Crater cracking at the end of the weld bead. Underbead underbed cracking, yes, that could be. And liquidus cracking, it is happening at the HZ. So answer will be underbed cracking and are the delayed hydrogen cracking appearing after the hydrogen diffused and stress buildup. Which of the following cracks are primarily associated with the fatigue loading after welding? So which is the that option A, toe cracking, Option B, crater cracking. Option C, solution cracking. Option D, liquidation cracking. Okay. So answer will be the option A, trough cracking. So trough cracks often initiate under the cyclic loading due to the stress concentration at the weld toe that results in the fatigue failure. So which parameter is most effective in reducing the underbreed cracking? So how we can prevent it? So generally cold cracking we can prevent it by preheating process. So if we increase the cooling rate, so if we do the preheating, what happens is that formation of the cooling rate will be reduces, so that it will reduce the formation of the martensitic phase, also allow to diffuse out the hydrogen. So option is the increase the cooling rate. If we increase the cooling rate means martensitic formation is more, so that is the not desirable one. B is the preheating. C, increase the sulfur content. If the increase the sulfur content, the more it is the more prone to um, it is more prone to crack formation because of it brittle phase formation. Okay. Next, reducing the weld size. If we reduce the weld size means uh, the smaller weld bit, that is also not a desirable one. So answer will be the preheating. So preheating reduces the cooling rate, that minimizes the martensitic formation, also allows the hydrogen to escape. Next, root cracking is more severe in which of the following condition? What is it? Low resistant, restraint and slower cooling, high restraint and faster cooling, low hydrogen content, D, high ductility microstructure. Answer will be high. Generally, root cracking is due to the high restraint, and if you do the faster cooling, that will accelerate this process. So, faster cooling results in the harder microstructure like magnetic, and higher restraint will result in the higher tensile stress. Both two will result in the formation of the hard root cracking. So, these are the some of the key points. Underbreed cracking, where it will happen at the HZ below the weld. So main reasons is that hydrogen plus martensite both are present. Okay, both are present. Next, toe cracking. It is at the where it will happen at the weld toe between the weld bead and the workpiece. It is due to the stress concentration. Root cracking. It is at the welding root due to the restraint and hydrogen presence. Okay, crater cracking, it is happen at the weld bead end due to the shrinkage, and fatigue toe cracking, it is at the weld toe it due to the cyclic loading. Okay, next, so chevron cracking. Okay, what is chevron cracking? You can see. So this is the chevron crackings. It is happens if you consider this is the weld bead, it is happens at the 45-degree angle to the both sides, 45-degree angle to the weld bead direction. Okay, why it is happening is that, no, where it is gone. So reheating or post weld heat treatment crackings are normally found in the heat affected zone, appears to restrict to the steel or weld material containing at least two two of these elements like chromium, molybdenum, vanadium, and chromium. Why is that? Because once we do post heat treatment, so that times this alloy contents will highly forms the carbides. It will highly prone to formation of the carbides. If the carbides are formed, the carbides are generally brittle, and it will be occupies at the grain boundary region, that will act as a starting point of the cracks. Okay. This is the normally found in the heavy sections and also in the coarser grain well metal and the parent steel. It is the typical problem in corrosion and heat resistance slow alloy steels. Alloying element affects the reheat crack susceptibility. Why it is the problem in the corrosion resistance metal is that corrosion resistance metals we generally add the chromium and nickel materials. Those components will react with the in steel. Carbon is there that will react more prone to react with the and forms the carpet that will results in the formation of the cracks. Okay, so we can calculate by using this formula what is the crack susceptibility mm, from for this kind of materials. So based on the what is the amount of the percentage of the we are having chromium, molybdenum and vanadium and so on. Based on that we can find out the reheat crack susceptibility. Okay, by using these formulas. Okay, so if it is less than greater than 0, it is the more susceptible to reheat cracking. Okay, so during the post weld heat treatment to the high temperature, it will generally at the 550 to 650. The elastic stress are relaxed quickly. However, the carbide precipitation occurs within the HZ grains. Okay, in the corrosion resistance low alloy steels. Okay, because of the carbide precipitation happens with like chromium carbide, molybdenum carbide, vanadium carbide, and so on. That will so as the grain becomes stronger, intergranule cracks occurs. Okay, so generally these carbides are much more stronger, but at intergranule region it is the less strength will be there. That will start the crack propagation. So along the prior to the austenitic grain boundaries in the HZ in the transformation steel, which allows any of the grain boundaries in the austenitic steel. So reheat cracks takes place at in different steps: formation of the nucleation cavities and the grain faces and its growth, and finally interlinking of those single facet cracks to form a crack several grain diameter long, which rapidly leads to fracture. So it is nothing but a formation of the small cracks. Those will be merged together and forms as a fracture. Okay. So this intergranule one once the intergranule region is less strength happens due to the stresses, residual stresses. Once it will easily exceed the its strength value. So their intergranule region cracks will be formed. Those will be merge with the other cracks and forms as a fracture. Okay, so which factors which will affect heat cracking is that one is the structure with the pure ductility. If the metal has a poor ductility, then it will form, and coarser grains if we have metal have the coarser grains. High heat input processes like slag welding, submerged arc welding, and so on, and high level of residual strain and preheating. Okay, if we give the preheating, then also there is enough time to carbide formation. That is also results in the um, reheat cracking. Okay, the problem of the reheat cracking is also occurring in the nickel based alloys and austenitic stainless steel because of the its this chromium and these elements tendency to form the carbides. Okay, the strain cracking is observed during the post well heat treatment of the heat and nickel based alloy during the solutionized treatment and both aging well stress relieved. Okay, so you can see here, so it is the it is the welding process. So here we do the solutionization. In the solutionization process, these carbides will again dissolved into the constituent elements. Then during the aging process it may form so crack occurs in highly restrained volumes when they are heated through the aging temperature range. Okay, so during the aging temperature range, so what happens during the aging temperature range? it is a formation of the carbides, and the carbides will results in the intergranular strength that will result in the crack formation. Okay. Preheat cracking because of the low ductility accomplished by the high strains at this region, and stress relaxation is reported to be smoother, more effective base metal region. So next we can see some problems with this one. Okay. So chevron cracks are typically associated with A. Solution cracking, B. Hydrogen cracking, C. Brittle fracture under tensile load, D. Liquidation cracking. So answer will be it is due to the brittle fracture under the tensile load. Okay. The chevron pattern indicates the brittle fracture propagation when crack fronts converge towards the origin, formation of the V-shaped patterns. Okay. The apex of the chevron pattern indicates the final fracture point, crack initiation site, maximum stress region, D. Heat affected zone. Answer will be B. It is the crack initiation site. As the chevron marking point towards the origin of the fracture helps to identify the where is crack started. Okay, it will propagate into the weld bit. Okay, so the chevron cracks is most commonly observed in the okay ductile material under compression, brittle material under tensile stress, high temperature creep condition, and fully austenitic structure. Okay, so answer will be the it is due to the brittle material under tensile stress. So you can see here. So once the high carbon content metal or brittle materials, once we do our tool steel materials, if we do the welding, so once it is started solidifying, uh, because of this brittle phase, tensile stress is generated because of the volumetric expansion, volumetric compaction is taking place. So because of that, this fracture will take place at the 45 degrees angle. That will that will result in this kind of cracks. Okay, those chevron patterns forms during the rapid brittle fracture, typically harder, low toughness material. Okay, next, which microstructure features promotes the chevron cracking in welds? Okay, so which is the hard and brittle material that will forms the this kind of cracking? Option will be A. Fine ferrite grains, B. martensitic structure, C. austenitic structure, D. perlitic structure. Answer will be it is the martensitic structure because it is the brittle phase and during the tensile load it will start cracking. Martensitic hard and brittle facilitate the crack initiation and rapid propagation that will result in the chevron pattern formation. Okay. Next, reheat cracking occurs during solidification, cooling to the room temperature, post weld heat treatment, and welding arc initiation. Answer will be C. Post weld heat treatment. So during the post weld treatment, the carbide formation happens and intergranular strength is reduces. That results in the formation of the crack, and when cracks are merging, forms the fracture. So reheat cracking occurs during the post weld heat treatment due to the stress relaxation and grain boundary weakening. Okay. Next, preheat cracking is most common in low carbon steels, austenitic stainless steels, creep resistance, low alloy steel, and aluminum alloy. Answer will be low carbon steel. We will not see because there is no carbide forming elements are there. Next, Austenitic stainless steel. Yeah, here also some of the chromium element are present, but compared to that one, creep resistance low alloy steels is the most prone one because they are having chromium, molybdenum, and so on. Those are most prone to grain boundary carbide precipitation that will reduces the ductility at the higher temperatures. Aluminum, no, aluminum it will not form. Okay. Next, each of the following is the primary mechanism of the reheat cracking. Option A, hydrogen diffusion. Option B, grain boundary sliding and cavitation. Option C, solidification shrinking. Option D, inclusion decohesion. Answer will be B, grain boundary sliding and cavitation. Okay, because of the at the grain boundary, segregation of the carbides will results in the brittle phase that will act as a crack initiation point. Okay. So during the post-weld treatment, stress relaxation occurs, grain boundary weakens, the cavities forms, and uh, it will be results in the crack formation. Okay. Next, reheat cracking are typically transgranular, intergranular, among the inclusions, random orientation. So transgranular, where we can see transgranular in case of cold cold cracking like hydrogen embrittlement. Intergranular is for the preheat treatment because of the segregation. Along the inclusion, it is for the laminar cracking and random orientation. No, it is not. It is the you can say like which cracking is that? Okay, okay. Next, it is the intergranular cracking. The reheat cracking propagate along the weakened grain boundaries, especially coarse grain HZ. Which factor increases the susceptibility to reheat cracking? Option A, fine grain size. Option B, low residual stresses. Option C, coarser grain HZ. Option D, low Li content. Answer will be C, coarser grain HZ. The coarser grains reduces the grain boundary area and increases the stress concentration, makes boundaries more vulnerable. Vulnerable. Okay. So it will be the coarse grain HZ. So in case of fine grains, we have the more amount of the grain area, but in coarse grains, we have the less grain area, intergranular region. So less intergranular region means it is the less path for the less area for the this carbides are to be precipitated out. So those will forms the crack propagation. Okay. Which preventive measure is more effective against the reheat cracking? Answer will be A, increasing the cooling rate, B, reducing the sulfur content, C, controlling the heat input and post weld heat treatment parameters, D, increasing the hydrogen content. Answer will be C. It is the controlling the heat input and post weld heat treatment parameters so that we can avoid this formation of the carbides and segregation, so that we can avoid the this reheat treatment reheat cracking. Okay, avoiding the excess grain growth and reducing the residual stresses and preventing the grain boundary weakening during the post weld heat treatment. Okay, so these are the some of the key factors which we can consider. Okay, for sevron cracking, we can see the V patterns of the fracture marks. That is the 45-degree angle to the weld bead direction. So location where we can see is that it is the fracture surface. why it is happening is that because of the brittle fracture. If the brittle phase is there, because of the tensile stresses, it will fracture. Okay, that results in the this kind of cracks. Reheat cracking, it is happening at the intercranial region location. If we have the coarser grains at the HEZ, that will result in this kind of reheat cracking. What is the reason? Because of the carbide formation and weak intergranular strength, and that will result in the and stress relaxation. Those will be the reason. Okay, post weld heat treatment. These are the reasons. Okay, coming to the final lecture of this week, that is of the laminar tearing and okay, stress corrosion cracking. Okay, so we can first quickly recap what is here taught by sir. Then we can see the problems. So laminar cracking or laminar tearing occurs in the HZ due to the combination of the localized stress and low ductility of the metal in through thickness direction. Okay, it is due to presence of the elongated strings of the non-metallic inclusions parallel to the rolling direction. So because of this if during the rolling direction, if there is any non-metallic inclusions are there, those will act as a starting point for the cracks, and that will be those are in the parallel direction to the rolling direction. And the crack initiation occurs because of the decohesion of the non-metallic inclusions near the well or just outside of the HZ, in or outside of the HZ. Okay, crack appears closely associated with the edge of the HZ. Okay, so this is how the laminar tearing looks like. So here is the weld bead and it is the HZ. Uh, so here we can see the parallel lines to the rolling direction due to the inclusions of the non-metallic elements. Okay. So what is the how major factors affecting this laminar tearing is that one is the type of joint we are doing, and what is the restraints we are providing, and what is the sulfur oxide contains in the weld material in the HZ, and type of the morphology of the inclusions in the base material, and hydrogen content of the weld, and use of the thick plates, preheating, and the strength of the materials of the electrodes which we are using. Okay, these are all are the factors which will affect this kind of laminar cracking or laminar tearing. Okay, so initiation of the laminar tearing is promoted by the factors such as the interfacial separation between the inclusion and metal, so and shattering of the inclusion itself, and presence of the submicroscopic inclusions, and silica and sulfate inclusions. Because of these inclusions, the cracks will generate and those will be propagate. The laminar tearing may also be due to bonding in direction of the rolling with crack appears in high carbon content zones. Okay, remedies might be use of the steel with low sulfur content, use of the steel treated with the rare earth metals, are reducing the hydrogen content and improve the weld joint design. These are the methods we can use to control this kind of laminar tearing. Okay. Next is the stress corrosion cracking. Why this stress corrosion cracking happens is that the many times because of the faster cooling of the well and alloying ingredients do not get sufficient time to completely mix and diffuse. Okay, those elements become tiny regions of the more highly alloyed than the bulk weld material. Because of the faster cooling, where the alloying elements are there, those cannot be diffused and forms as a tiny. Mm, okay, okay. Often those are the martensitic structure which can give the problem in service with the stress corrosion cracking. When carbon steel weld welded joints are exposed to severely corrosive conditions. Once such kind of tiny regions where high alloy content is there, and once we expose this to the corrosion environment, those will be forms as a starting point for the corrosion to be happens. Once the corrosion happens, the material is depleted, then the cracks will start appearing. So when the carbon steel welded joints are exposed to the severely corrosive conditions, there is a tendency of attack on the weld metal or HZ, and the life of the weld metal may reduce. Okay, so those stress corrosion cracking of the HZ of the weld occurs if the weld joints that have the not been stress relieved are exposed to the aqueous solution of the hard concentrated uh, caustic soda, and weld metal is subjected to the high tension level. Okay, those cracks in in carbon steels typically intergranular, while they are the transgranule in austenitic stainless steel. Okay, generally in carbon steels we can see the intergranular cracking, but in case of austenitic steel we can see the transgranular cracking. Okay, because of this stresses, if we do not to relieve the stresses and we use the material directly at the corrosion medium, the stress region will highly prone to the corrosion, and that will reduce its materials life cycle. Okay, so we can find out the, if we have the this kind of concentration is increasing more, the we can see the stress relieving we required to do or not, we can find out from here. Suppose if the soda content in this aqueous solution is less than 10 or 20%, we can safely operate that one. Even the stress without stress relieving, we can operate up to 80 degrees centigrade or like that. But if the soda content is increasing, we must perform the stress relieving operations to use them, so that use them in the highly corrosion medium like salt water, sea water, and so on. Okay, so this is how the stress corrosion cracking looks like. Okay, for the carbon steel, uh, sodium and ammonium nitrates are important stress cracking agents. Apart from the cyanides means nitrates, and sulfides, and coal gas liquids. Okay, those are the limited concentration and temperature values are above which stress relief of the joint is required. Okay, in welding austenitic stainless steel, severe residual stresses are caused due to low thermal expansion coefficient. Okay, upon exposure to the um, chloride containing corrosion medium, stress corrosion cracking may arises. Okay, so with this we can see some of the problems. Okay, so laminar tearing is primarily observed in weld metal, fusion zone, base metal in parallel to the rolling direction, or HZ. Answer will be C. It is the base metal region. So laminar tearing occurs in the rolled steel plates due to the elongated inclusions aligned parallel to the rolling plane. What is those kind of inclusions? Like sulfates, phosphates, and other non-metallic elements, oxides, and so on. Okay. So the main cause of the laminar tearing is hydrogen embrittlement, sulfur segregation at the grain boundaries, non-metallic inclusion, carbide precipitation. So hydrogen embrittlement we can see in the cold cracking region, sulfur segregation we can see in the solidification cracking, carbide precipitation which we can see carbide precipitation which we can see in the post weld heat treatment to cracking, and non-metallic inclusions we can see in the this laminar tearing. Okay, such as manganese sulfate and so on. Okay, next. Laminar tearing occurs due to longitudinal shrinkage strain, throughout thickness tensile strain, compressive stresses, D. Thermal expansion. Answer will be B. It is the through thickness tensile strain. Okay. The shrinkage stresses acts perpendicular to the plate surface, causes separation along the inclusion layers. Okay. So which weld configuration is most susceptible to laminar tearing? So which weld configuration? Butt joint, lap joint, T joint, edge joint. Answer will be, it will be the T joint. Okay. Why is the T joint produces the high throw thickness strain that makes them more prone to laminar tearing. So which is the preventive measures to reduce the laminar tearing? Okay, what is the how we can reduce is increase the sulfur content. If we increase the sulfur content, what happens? It will increase the non-metallic content, then that will increases the laminar tearing more. So that is not using the cleaner steel without the with low inclusions. If there is no inclusions, means less laminar tearing will happens. Okay. Option C, increase the cooling rate. If you increase the cooling rate and a brittle phase will form, that is also will act as a will not the good for the crack mitigation. Option D, reducing weld penetration. If we reduce the weld penetration, that is also not. So option will be B, using the clear steel with low inclusions. So reducing the inclusion content will result in the improving the throw thickness ductility. So that will reduces the laminar tearing problem. Okay. Next, stress corrosion cracking requires only tensile stresses, only corrosion environment, both tensile stresses and corrosion environment, or compressive stress and inert environment. Answer will be, it will be we require both stress and the corrosion environment. Okay. So this the stress corrosion crackings occurs due to the synergy of the interaction of the tensile stresses and specific corrosion medium. Which type of the crack morphology is commonly observed in the stress corrosion cracking? Which kind of we can see dendritic structures, intergranular or transgranular, strap-like, or chevron pattern? Answer will be intergranular and transgranular. Okay. Why? Stress corrosion crack propagates along the grain boundaries, intergranular region, and through grains, transgranular, depending on the material, environment, and combinations. Okay. Next, which of the following environments are known to cause the stress corrosion cracking in the steels? It is nothing but asking the what kind of corrosion medium. Dry air, dry air is not that much corrosion medium. Pure nitrogen, that is also not a corrosion medium. Chloride containing solution, yes, because current is a very corrosive environment. Vacuum. So answer will be C. So chloride ions are aggressive and can be induced the stress corrosion cracking is main in many alloys, including the stainless steels. Okay. Which factor increases the susceptibility of stress corrosion cracking in welds? Option A, compressive residual stresses. Option B, low temperature. Option C, tensile residual stresses. Option D, fine grain size. So answer will be tensile residual stresses. Why? Residual tensile stresses from welding acts as a driving force for the stress corrosion cracking even without the external loading. Okay, which prevent method effective against the this stress corrosion cracking? Increase the residual stresses, use the compressive surface stresses, increase the inclusion content, rapid cooling. Option will be use the compressive stress surface stresses. That is nothing but if we do the short pinning operation, that will reduces the that will induce the compressive stresses, that will reduces the stress corrosion cracking. So short pinning introduces the compressive residual stresses and counteracting the tensile stress and reducing the stress corrosion cracking susceptibility. Okay, so these are the some of the key factors. So in case of laminar tearing, where it will happen at the base metal region, why it is happening? Because of the inclusions and strain. And next, which direction it is happening? It is happening throughout the thickness. And nature, it looks like in a step like cracks. And how we can prevent is that clean the steel surface and buttering layer, and if we reduce the amount of the non-metallics in the material. Okay, next coming to the stress corrosion cracking, where it is happening at the weld bead, heat affected zone and surfaces. Why it is happening? Because of the stresses and the corrosive medium both. And at how it is happening, it is along the and throughout the grains. And how it is nature, it is intergranular and transgranular. How we can provide that one is that stress relieving operation and environment control. Okay, these are the all about the today class. Okay, so any further to discuss, we can discuss.